a week, so I'm going off to Italy tomorrow morning, and Germany, Poland, Walls. Stack as well, just with sit down then and you. Yes, yes.
Good afternoon. On behalf of the Southampton Theory, Astrophysics, and Gravity Research Center, STAG for short, I would like to welcome you to this public event. My name is Kostas Kenderis, and as the director of the STAG Research Center, I will be your host today. So before we start the lecture, I have one announcement for the fire and safety. So if there is a fire alarm, please stay where you are, and then the ushers for technicians would come and direct you. And then next, I would like to say a few things about the STAG Research Center. So STAG was formed in 2012, and it grew out of 3 successful groups. The gravitational group in mathematical sciences, and the high energy and astronomy groups in physics and astronomy. And its mission was and still is to foster and promote research, cutting-edge research in the front line. And our ultimate goal is really to understand the laws of nature from the very small to the very big, to go from the fundamental constituents of matter to the galaxies and the universe as a whole. And this understanding demands and promotes synergies among many different disciplines and requires new ideas and new mathematics. And such synergies can only be achieved through a center such as STAG. So the University of Southampton has made many important contributions in fundamental science. And our studies range from studying the quantum laws of microcosmos, the study of elementary particles and their interactions, to the quantum origin of the universe. Is our universe a hologram? Is it made out of tiny little strings? To studies of black holes and neutron stars, because these extreme environments power some of the most spectacular phenomena in our universe, to the large-scale evolution of our universe. What drives the evolution of a universe? Is it dark energy, what are they? And we also actively engage in high-profile international experiments and observational facilities. We in STAG very strongly believe that it is very important to engage with the general public with what we do and to promote public understanding of fundamental science, and perhaps more importantly, to inspire the students of today to become the scientists of tomorrow. And for this reason, part of our mission is to also organize an annual event every year where we have a distinguished guest that explores and explains some of the greatest achievements in fundamental sciences in recent years. So we were very fortunate to have Lord Martin Rees, the Royal Astronomy, to deliver the STAG lecture in 2013, and Professor Hera Toft, 1999 Nobel Laureate in Physics, to discuss the origin of mass in last year's STAG lecture. And we're also delighted to have this year Brian Schmidt, the 2011 Nobel Laureate in Physics, and the Diamond Jubilee International Fellow at Southampton, to deliver this year's lecture. Finally, it is my pleasure to now invite our Vice Chancellor, Professor Sir Christopher Snowdon, to introduce our distinguished guest.
Thank you very much. Well, thank you very much, Kostas. I'm exceptionally pleased and honoured to introduce our speaker, Professor Brian Schmidt, Laureate Fellow and Distinguished Professor at the Australian National University's Mount Stormio Observatory, and a University of Southampton Diamond Jubilee International Visiting Fellow, of course. Quite a mouthful. More importantly, of course, he's about to become a Vice-Chancellor and President himself, so I think he'll discover shortly the challenges that brings. Professor Schmidt was born and raised in Montana. He did his undergraduate and MSc studies in physics and astronomy, and he has a PhD from Harvard University under Robert Kirshner. He says that his acceptance to Harvard was the best birthday gift of my life, so I can understand that. He joined the Australian National University in 1995, and as I say, he's just gone on to take up the most senior role there. In 1994, with Nick Suntseff, he formed the High-Z SN Search Team, which is a group of 20 astronomers on 5 continents. and they used distant exploding stars to trace the expansion of the universe back in time. The group's discovery of an accelerating universe was named Science Magazine's Breakthrough of the Year in 1998. The team went on to share the 2007 Gruber Prize for Cosmology and 2014 Breakthrough Prize in Physics, a phenomenal achievement in its own right. In 2011, Professor Schmidt won the Nobel Prize in Physics, jointly with Adam Rice and Paul Perlmutter, for the discovery of the accelerating expansion of the universe through observation of distant supernovae. So you'd think at that point in time you're kind of done with all the difficult things, but he's continuing his work working on supernova and the life of stars to study the universe. He leads Mount Stormio's effort to build a Sky Mappers telescope, a new facility that will provide a comprehensive digital map of the southern sky from ultraviolet through to near-infrared wavelengths. He also runs the My Perneri Vineyard and Winery, clearly a key part, and I understand this was all part of the deal in becoming a Vice-Chancellor. So I want to know, where is my winery? It's a small winery, but it does produce Pinot Noir, so I can imagine it's very popular as well. Professor Schmidt's talk, The Accelerating Universe, is going to describe his remarkable discovery that the expansion of the universe is accelerating. He's going to talk about the observations that have led astronomers to trace the origins of the universe back more than 13 billion years. And when combined, how such research now leads astronomers and scientists to ponder the ultimate fate of the universe. We look forward very much to hearing more about this. So, ladies and gentlemen, Professor Brian Schmidt. Thank you. Thank you.
Thank you, everyone. Make sure we're, yes, great. Thank you, everyone. It's a great pleasure to be here in Southampton. Being a Diamond Jubilee Fellow is allowing me to work with Mark Sullivan here, who is one of the stars in our field and sort of the great astronomer of his generation in my area. So it's a great honor to be able to work here with him. And I hope you treat him well, because he is a great guy to have around. Anyway, my talk today on the accelerating universe is a discussion not just of our discovery, but to understand it, you're going to really need to understand the universe from beginning to end. And so today, hopefully, we will get across all the concepts of modern cosmology, all in about 45 minutes. So hopefully you have your seatbelts well and truly fastened. So let's first start with a tour of the universe. Now, when we're going to take a tour of the universe, we're going to use the speed of light as our guide. Speed of light is 300,000 kilometers per second. So that means going around the Earth 7.5 times in 1 second. And now let's go out from the Earth and think what that means. For example, if we move the first step in our sky to something we see, well, that's the moon. And when we look at the moon, we're looking back about 1.5 light seconds. So when Neil Armstrong took his one small step for all of us, we found out about it 1.5 seconds later. The radio waves transmitted, traveled for just under 1.5 seconds, landed, it turns out, on a radio dish about 40 kilometers away from where I live, about 15 kilometers away from where I work in Australia, and then were broadcast around the world. When we look beyond the moon, we sometimes forget how big things are. For example, the sun. The sun's about 5 light seconds across. It's much bigger than the Earth-Moon system. Of course, the reason the sun looks the same size as the moon, very convenient for solar eclipses, as it turns out, is because it's a lot further away. It's about 8 light minutes away. Looking out even further, we can look in Australia to the nearest other star, Alpha Centauri. And so when you come to Australia next time, I hope most of you will come at some point in your life. It's a good place to visit. The Australian government provides me a small little sum whenever I advertise. You can see Alpha Centauri, the nearest star system to our own. It's a very bright star, and it points conveniently to the Southern Cross. Now, Alpha Centauri is actually 3 stars, 2 very close to each other, both about the same mass as our sun, which means they're about the same size. So let's think what 4.3 light years is. 4.3 light years is light traveling 300,000 kilometers per second for 365 1/4 days 4.3 years of that, each one of those days having 86,400 seconds. It's a long ways. As an analogy, we could imagine our sun. Let's just say I have the sun here as a football, or as a soccer ball, as we'd say in Australia. Football being something more that we refer to rugby, and that's not the shape of a star, so a football. And we think, if the sun is here, where would Alpha Centauri be in a scale model? And if the answer you got was Canberra, Australia, where I'm from, you'd be about right. That's the scale of the universe, with all that space in between us being empty, or nearly empty. What is quite remarkable is we live in one of the most exciting places in the universe, a galaxy called the Milky Way. A galaxy that has 100 billion stars, not unlike our sun, which is about 100,000 light years across, is orbited by a galaxy, the Large Magellanic Cloud, that's 185,000 light years in distance. And that is what we call a dwarf irregular. It has only 10 billion stars. There's another little one, the Small Magellanic Cloud, has 1 billion stars. Those are the little tiny cockroaches of our universe. When you come to Australia, you can see those as well. And the Large Magellanic Cloud from a dark site really does look like a spiral galaxy. It's quite remarkable when you can see it. If we go even further, well, what do we see? So let's zoom in on a piece of sky smaller than the moon. So if we look at a tiny little piece of sky that the Hubble Space Telescope conveniently looked at for several weeks, what do we see? Well, we see back about 12.5 billion years into the past. We're looking at stuff whose light has taken 12.5 billion years to reach us. These are the most distant objects that we can see right now in the sky. But we can see even further. We can look back 13.8 billion years into the past now, to a time when the universe was hot. Hot 3,000 degrees Celsius, glowing like the sun. Here's that picture. We call this the cosmic microwave background. And before that, well, that is the time called the Big Bang. So, how did we figure this out? Let's go back to the beginnings of cosmology. Cosmology really started in about 1915 or 1916. Two things happened. First, the beginning of observational cosmology. That's what I do. It's where you use telescope to look at things. And that was done by someone who you probably haven't heard of. His name is Vesto Melvin Slipher. And what he did is he took the light of stars and formed a spectrum. But rather than a star, he looked at a galaxy. Now, in 1916, when he did this, we did not know what a galaxy was. And he looked at it and he said, well, it looks a lot like the same stuff that a star is made out of. But there was a difference. And that difference was that the light was stretched redward. And he knew what could do that. It's called the Doppler Shift. So, for example, if you have a police car going towards you and its siren is going, its sound waves are compressed, means the pitch is raised. As it goes by you, the sound waves are stretched and the pitch is lowered. Light, of course, is a wave. It's a little different than a sound wave, but the same basic rule applies. And so if you have a galaxy whose light is stretched, that means it is moving away from you by how much the light is stretched compared to the speed of light. And so what Slipher found was quite remarkable. He found that almost every single galaxy in the sky was moving away from us. This was a cosmic conundrum in 1916. Because since the time of Copernicus, we had sort of developed the idea, the comfort with the idea, that we were not in a special place in the universe. We were in a place like any place else. And suddenly, this observation came along, which indicated we were in a special place, a place where these galaxies were moving away from. This did not make sense in 1916. Well, it turns out it eventually did make sense, because by measuring distances to those galaxies, and that was something that Edwin Hubble did with the largest telescope, the 100-inch at Mount Wilson, you can still go and visit, he was able to look at the stars, and he knew the further a star was, the fainter would appear. And so by looking at how bright stars were in galaxies, he could roughly judge how far away each galaxy was. And so when he did that, he found something remarkable. He found that the faster the galaxy was moving away from us by Slipher, the fainter its stars. In other words, the further the object, the faster the motion. And this is what his data looked like in 1929. It's always good to see what profound discoveries look like. That's what they look like. You go through and you measure how bright stars are. The bright stars have slow motion. The faint stars, the galaxies, have lots of redshift or fast motion. And on the basis of that, he announced to the world that that meant the universe was expanding. Now, why did he say that? Well, think of a cartoon. Here's the universe, which, thanks to the wonders of a computer, I'm going to expand. Now, let's overlay before and after. So I'm going to take the first image and the after image and see what I see. So we go through and take the first image, overlay the second image, and you can see the nearby objects, when I've expanded my universe, have moved a little bit. If I was measuring their velocity, it would be low. The distant objects, well, they've moved a lot more. Their velocity would be high. And it doesn't matter where you are in the universe. I can overlay these pictures anywhere, and I see exactly the same thing. So an expanding universe is what Hubble saw, consistent with an expanding universe. Now, it turns out that Einstein was also working in cosmology at the same time. Theory was very different than observational astronomy at the time, and so it wasn't very well informed. But in 1907, Einstein had what he described as the most happy thought of his life. Only Einstein would have this be his most happy thought. He was watching someone fall off a roof, and he thought, wow, I bet you they don't feel any gravity at all. And then he thought, I bet you that gravity and acceleration due to gravity and acceleration due to moving faster are always offsetting each other exactly. That is, there was no way of discerning the difference between the two. Put another way, if I put you in a box, you can't tell if you're in a rocket accelerating at 9.8 meters per second squared, or if you're just sitting on Earth in the box being accelerated by gravity. They are absolutely equivalent. That's a tiny little thought, but one that took Einstein 8.5 years to sort out. And in the end, he came up with his theory of gravity, which predicted that space would be curved, but it also, and it turns out you could go through, and Eddington went through and showed this through eclipse pictures where we looked at the displacement of stars behind the sun during an eclipse, and it turned out to show that Einstein's theory was the correct one. It was not what Newton's laws would have predicted. And this curving space allowed you to think of the universe in a different way. But it also allowed you to do things in cosmology. One of the problems that Newton had is if you take Newton's laws and you imagine a universe that goes on without end, there is no solution for the universe except for an empty universe. And this drove Newton nuts. And Newton, if you ever get a chance to go to Cambridge and look at his little books, was a nutso guy, as pretty well indicated from his notebooks, which he did in as many decimal places as he could fit across the page, about 60 most of the time. Imagine what the guy could have done if he had only kept 3 or 4 significant figures. All right, so Einstein applied his new gravity to the universe, and what he discovered is that the universe should be in motion. That was a problem because he looked around and the universe around him in 1917 when he did this work, and it looked static. So he did what any good theorist does when their theory does not meet observations. He added a fudge factor. And that fudge factor is known as the cosmological constant. You can think of it as the energy that is part of space itself. And under his equations, this energy pushes on space or itself, and could be then, therefore, counteracting the attractive force of gravity. Of course, in 1929, when it was realized the universe was expanding, he described it as him acting like a donkey, often described as his greatest mistake. Now, when we talk about the expanding universe through the lens of Einstein's theory, you think about things a little differently. You don't think of objects moving away, but when you look a long ways away, you're looking back in time, you're looking at space which is expanding between us. So as light travels through the expansion of space, the light gets stretched. So it's not so much that objects are moving away from you, it's that space is being created between you. That's a slightly different way of thinking about it. You can get into endless arguments with some physicists about whether or not there really is motion of the creation of space. I think it's easier to understand it this way, and it's certainly the way Einstein thought about it, as near as I can tell. So light is stretched as the universe expands. So let's think what this means. The universe is expanding. Let's run it in reverse. There will be a time when the universe in the past will be smaller than it is today, at least our part of the universe, and things will be closer. The universe will be hotter. You inevitably get to a time when everything in the universe is on top of everything else, the time of the Big Bang. If the universe is expanding, it's sort of inevitable that there was a time when everything in the universe was on top of everything else. There are ways to get around that and have material created out of space itself, and that was something, for example, that Fred Hoyle believed in. But the Big Bang is the logical conclusion, and it was first thought of in about 1931 by someone who actually discovered the expansion of the universe in 1927, Georges Lemaître. And so poor Georges Lemaître figured out the Big Bang in 1931, measured the expansion of the universe in 1927, and almost none of you will have heard of him. So he's an unsung hero. Sometimes science is not fair. I don't think Georges actually cared that much, but most people would have been pretty bitter and twisted missing out on those two things. So let's think graphically about an expanding universe. Right now, you have two galaxies. I run the universe in reverse on that trajectory, and when I go back, there's a time when they're on top of each other. That's the Big Bang. Now, the steepness of that line is how fast the universe is expanding now. We call it the Hubble Constant. It's the distance of an object divided by its redshift, and allows you to measure how old the universe was. So when I went off to Harvard, that seemed like the coolest project I could possibly do. Measure the age of the universe. And so that's what I did, and here I am looking at the age of the universe with my PhD supervisor, 1993, 3 years, 11 months, and 4 days after I started, but I wasn't counting. And what did I find? Well, I found that the age of the universe was about 14 billion years. Other people were working on this, and I'm sorry to say that although I got about the right answer, I don't get credited for discovering the age of the universe. I was one of many people who was working on this. But all of us had cheated a little bit in figuring out the age of the universe. Why? Because that line is straight. And we know the universe is full of stuff. We don't know how much, or at least we didn't back then, but we knew that gravity of all that stuff would pull on everything and slow the universe down over time. And so we wouldn't expect that line necessarily to be straight. It might be straight if there wasn't much stuff in the universe, but if there was a fair bit of stuff, then the universe would be expanding faster in the past and slow down, meaning the universe might not be nearly as old as we would otherwise think. For a perfectly reasonable amount of material, the universe, instead of being 14 billion years old, might only be 10. And 10 was a problem back then because 10 billion years was clearly a shorter amount of time than the oldest stars that lived in the universe. And we astronomers are not too picky, but we do like the things in the universe to be older, or to be younger than the universe, not older. And that number, that specific number, of having the universe only be 10 billion years was the preferred value by theorists who had a very specific value for how much stuff there should be in the universe at that time. So that's a problem. But it also has kind of profound consequences for the future. Why? Because imagine a universe that doesn't have much stuff in it, so it's not slowing down. It gets bigger and bigger and bigger over time. It's a universe that expands forever. It's a universe that is infinite into the future. On the other hand, if the universe has a lot of stuff in it, then it might eventually stop expanding and then go in reverse if it has enough material. So all universes begin with a Big Bang, but only a heavy universe ends with a Gnab-Gib, which is the Big Bang backwards. All right. The slowing down as a review of the universe affects how old we think the universe is. It tells us the ultimate fate of the universe. And it turns out it also tells us then the shape and weight of the universe. Space is curved under Einstein. So if you have a heavy universe, a universe heavy enough such that it will eventually stop and go in reverse, well, that universe turns out to be geometrically bent onto itself, so it's finite. Not only does it finite in the future, it's finite in its volume. It wraps onto itself, unfortunately in a fourth dimension. What's that mean? It means if we live in such a universe, you go here, you head out that direction, give it enough time, you come back, if you're, for example, a photon, where you started. You're maybe saying, I don't understand how that works. Well, that's the problem. We're not very good at visualizing 4 dimensions. I like to say that I have never met a sane person who can visualize 4 dimensions, and you do not want to be one of the people who can. Now, a light universe bends away from itself in the shape of a saddle. Triangles in this universe have angles that add up to less than 180 degrees. In a universe that's finite and heavy, triangles add up to more than 180 degrees, just like they do here on Earth. Now, you've probably all been thinking, I thought triangles add up to 180 degrees on Earth. Well, sure, if you're in this room, but if you go out and get a globe and look at the entire universe, do a big triangle on Earth, then you'll see that the triangle adds up to more than 180 degrees. So one of the ways that you can go out and actually measure the geometry of space is to measure angles of things across the universe on very, very large scales. And that's effectively what we have done, as I'll show you at the end of this talk, to measure the shape of space. And finally, we have the just right universe. The universe precariously balanced between the finite and the infinite. A universe which sort of more or less goes on without end, and triangles add up to 180 degrees. It's just right because theorists trying to understand the earliest times after the Big Bang have been convinced since about 1981 that the universe should be just right. Now, one of the things that an observational astronomer likes to do is to go out and show theorists wrong, because theorists are really cocky. What I have learned in my life is theorists are pretty smart, so you got to be careful with them. So, what can we do? We can go out and measure what the universe is doing back in time. So when I moved to Australia in 1995, I came with a fresh project. A project to go through and measure how fast the universe is expanding now and compare it back in time. Now, if the universe is expanding at the same rate in the past as the present, then you know that the universe is just coasting along. It's essentially empty. On the other hand, there is a trajectory which, if the universe is slowing down faster than that line, then that means gravity is going to eventually win and the universe is finite. The other side of that line, well, then gravity loses and the universe continues expanding forever and it's infinite, the shape of a saddle. A great experiment, but it means we have to look into the past. And to look in the past means looking very, very far away, which means something really bright and really big sensitive telescopes. And all of those ingredients came together, it turns out, in 1994. And the first ingredient is something really bright, type 1a supernovae. So what's a type 1a supernova? To understand a 1a supernova, let's look at the life history of our sun. So our sun, about 4.55 billion years ago, was born. And in the future, our sun is going to start to grow in size, and eventually it's going to collapse down when it runs out of nuclear fuel, destroy the Earth, and collapse down to a tiny little star known as a white dwarf star. Now, if our sun was instead born as two stars together, very close, then something different can happen. And so, in this case, you can imagine that if they're close enough, the first star, when it puffs up and starts running out of nuclear fuel, can donate material to the smaller star, making the smaller star, interestingly, heavier than either star. Now, that new heavy star is going to burn through its material, it turns out very quickly. And as it burns through its material, it's going to effectively be able to start donating material to the first star. And so here we have a white dwarf, which is just like what our sun would do, with this new sun with lots of material on it, and it can donate material to the white dwarf and make it heavier. Chandrasekhar won a Nobel Prize for realizing that if you take a white dwarf star and you make it heavier than 1.383 times the mass of our sun, it is going to run away from gravity, and it turns out instead of becoming a black hole, it's going to explode as a giant thermonuclear bomb. A bomb not the size of a suitcase, but the size of our sun and beyond. This creates one of the largest bangs in the universe since the big one, known as a type 1a supernova, an object that produces 6/10 of the mass of our sun in iron. 2/3 of the iron in the universe, the iron you're sitting on in these seats, the iron that is making Australia still a relatively rich country, despite the recent commodity price decrease. Well, this iron is created in these exploding stars. I keep on trying to tell some of our iron magnates that they should want to do research so they understand the source of their wealth, and thus far they have decided to keep their wealth to themselves, but I'm working on it. So these exploding stars are bright. They're 5 billion times brighter than our sun. A group in Chile that I worked on with my PhD thesis, well, they went out and tried to understand these objects. And what they found is they were not all identical. Some were brighter than average, and some were fainter than average. It turns out the brighter than average ones produce more iron, and they rise and fall more slowly than the ones that produce less iron. And so by calibrating how fast they rise and fall, you can very accurately measure their distances. And this discovery was made in 1994 when Mario Hamwi from that team visited us up in Harvard and showed us his work. Now, this work happened a year after my PhD and allowed that group to make a measurement on the expansion rate of the universe that was much more accurate than what I could make. So I was rather glad it happened about 9 months after my PhD. But as my friends, I said, hey, we can do the big experiment because something else has happened. And that something else that's happened is there was a new generation of telescopes, the Keck 10-meter telescopes, the first telescopes large enough to allow us to reliably look back and discover what the properties of these exploding stars would be like and get their redshifts back, let's say, halfway to the edge of the universe. Finally, there was one other ingredient which we all have benefited from, which is the development of large format digital cameras. So in 1994, we got our first 4-megapixel cameras. And we're all used to these things now because we have essentially a derivative of these things in our phones. But that, in 1994, allowed us to find these exploding stars because they're very rare. And these digital cameras are 100 times more sensitive than photographic film. So you needed them, despite how bright these objects are, to discover the distant objects, and you needed to have enough megapixels to actually find enough of these. Finding these objects turns out to be quite challenging. A group at Berkeley in 1994 was the first to find. They found 7 objects in 1994. And as that was happening, I was down in Chile with Nick Sunsev, shown here, and we were discussing using their new supernova technique to go out and measure the expansion rate back in time. We knew the Berkeley group was doing this as well. We had talked about working together. They were a particle physics team. We were a bunch of astronomers. We'll just say that we didn't see eye to how to do the experiment, and we decided, well, I guess we'll do it ourselves. And thus our team was born, and this team is quite remarkable because I was 27 years old, and my colleagues, almost all of them tenured, all the people who wrote my letters of recommendation, allowed me to be the leader of this team. And it's a great tribute, at least to them, from my perspective, that they gave me that honor at such a young age. So, as I said, there were 2 teams. We were very competitive. Saul Perlmutter there on the right and me, a younger me, were well known in the media for sparring. Not the 2 of us so much, but the 2 teams. We had some bigger personalities than Saul and me on our 2 teams, and they were well known for having it out. It's very competitive because you need telescope time, and telescope time is in short supply the world over. And so we would have to go through and try to get enough telescope time to find the supernovae. And it was quite challenging to find these supernovae because we would take upwards of 50 gigabytes of data in 1995, back when we were using Pentium 200s, if people remember what those are, and we had massive 1 gigabyte hard drives. And I didn't have a big budget. My budget for the Accelerating Universe was $8,000 Australian, so about, at the time, 2,500 pounds. And so we went through and sort of daisy-chained every hard drive in Chile together when we were doing this work, and we had to write the beginnings of essentially software to plow through all this data and find the needle in the haystack, because in all this data there would be a couple objects like this one, a supernova, which we know is a supernova by taking a before and after picture, and you can see nothing become something. Now, this particular object was 5 billion years in the universe's past. It exploded before the Earth was formed. That is the power of astronomy and cosmology. To give you a sense what it's like, let me take you to the Saratollo 4-meter telescope in the 1990s. This telescope, as the sun sets, you can look out. That's Greg Aldering from the other team. He's silhouetted in black because he's the bad guy from the other side. Why is he there? Because he's going to use the night after us. Because this is the telescope with the big digital camera on it that is really the only facility in the world capable of doing this in the 1990s. There we have the data coming in, and my software, not particularly good software, but adequate to the purpose, is sifting through this data, trying to find the needles in the haystack. Now, we were using the beginnings of artificial intelligence. It wasn't very intelligent, I'm afraid. And so we literally had a sweatshop of astronomers in there trying to discern the wheat from the chaff. And so time is of the essence because we also have time on the big Keck telescopes in Hawaii just a day later. And so we have to process all that data, find the interesting objects, send them to Hawaii, where Adam Rees and Alex Filippenko would be able to go and get a redshift and a spectrum of these objects. But of course, there is Saul Perlmutter. Why? Because he needs to use the Keck telescopes too. They're the only ones in the world capable of doing the experiment. So although we're very competitive, we also get to see each other on a regular basis. So, 3 years later, Adam Rees, who was the youngest person on our team at the time, sends me a diagram that looks more like this. Each exploding star is an error bar on this diagram. It gives a measurement of how fast the universe is expanding at that time. So it's 2/3 of the time, the way an error bar works, 2/3 of the time, the correct answer is within the error bar. And so you have to go through and compare the nearby objects with the distant objects. And when you look at the distant objects, the first thing I saw in this diagram is not a single one was consistent with the bottom of the diagram where gravity wins and the universe is finite. That rather saddened me because, I don't know, I kind of liked a universe that had a beginning and an end. It's something my poor little brain could understand. Trying to stay away from infinity is always useful to a poor little brain. But as I've discovered in life, the universe doesn't care what I think, it does what it wants. The next thing I realized is, on average, those distant objects were not in the yellow part of the diagram. Rather, they were at the top part of the diagram. The universe appears to have been expanding slower in the past and has sped up over the last 6 billion years. Now, people often ask, when you saw this diagram, did you go, eureka, yeehaw? The answer is no. I called up Adam, and I said, oh, Adam, what have you done? And for the next several months, Adam and I went line by line through each of our code, and we tried to sort out what could have possibly gone wrong. But at the end, after several months worth of work, it became clear that the answer was not going to go away. And so we had to, in 1998, tell the world about this, we didn't call it discovery, we called it evidence that the universe was accelerating. I knew what our data said, but I wasn't absolutely convinced what it meant, because I knew, in the words of the modern day philosopher extraordinaire of the United States, Donald Rumsfeld, that we had controlled the known unknowns, but the unknown unknowns are always scary. And when you get a crazy answer like this, you got to worry about the unknown unknowns. And so you can never know the unknown unknowns. And so you go forth and say, well, this is what we see. Well, it is that work that led to these two papers, because it turned out, unbeknownst to us, Saul Perlmutter's team was getting the same crazy answer that we were. And so the two teams in 1998 announced our joint measurements of essentially the same thing. And it's for that we won our respective Nobel Prizes. Here we are, the High-Redshift Supernova team, together for the only time in its history at the Nobel Prize ceremony. I should say, for those in the audience who noting it's a fairly blokey team, as we would say in Australia, it was. And that sort of reflects cosmology in, especially in supernovae, the area I work in 1995. The good news is that we haven't quite reached gender equality yet, but we do have more than 1/3 of the people in our field now as women. And so that is a place where we have needed to change, and hopefully we'll continue to change in the future. Saul Perlmutter's team was also there. They had a little bit more gender balance than we did, but together we were able to celebrate in Stockholm this piece of science that we're all involved in. And from our perspective, I guess it's quite remarkable to me that Sweden decides as their big event of the year to celebrate science, and that's something I think the entire world can thank them for. Now, one of the things that no one ever told me about is, what is it like to win a Nobel Prize? And so, for when you win your Nobel Prize, I'm going to give you a little insight. So the first thing is, when you land in Stockholm, you do not have to go out the front of the airplane with everyone else. They're going to allow you to go down the steps and be picked up by someone. In my case, this guy, who introduced himself as Stig. And I said, Stig? This is going to be interesting. So Stig got us around the streets of Stockholm very quickly. Great driver. You get to meet the king. The king is very serious. I brought him a bottle of wine, sort of expecting him to put it away in the cellar, but he had actually, when I was up there, he said, thank you for the bottle of wine, it was very good, we had it last night for dinner. That's what he said to me when I was up on the stage. It was quite nice. And what I really like about the Swedes is they lend you their princess. I could say something rude at this point, but I'm not going to. The Swedish princess, Crown Princess Victoria, is very, very conversational, and it's quite a remarkable person. But she certainly provides a certain amount of glamour as for the average Nobel Prize winner, quite unlike anything else you ever experience in your life. So, what is pushing on the universe? Why is the accelerating universe so interesting? It all comes down and back to Einstein. That is, Einstein's big mistake, the cosmological constant, his fudge factor, explains exactly what we are seeing in the universe. That is, we need to have energy that is part of the fabric of space, and then gravity will make that stuff push against itself rather than attract. The only problem is we need to have about 70% of the universe be this stuff that pushes. We also still need 30% of the universe to attract, and we need to have a little bit of a balance. That is what our measurements in 1998 said. So, as I said, the unknown unknowns. So what do you need to do? You need to go and do another experiment. And other people did. And one of the things that was done was a joint Australian English program known as the Anglo-Australian Redshift Survey, which went out and mapped 221,000 galaxies. And that foam structure you see there is caused by gravity. So it allows you to essentially weigh the universe. So what you do in practice is you model the universe in a computer, and then you observe the universe. And so if you look up there are 4 models of the universe, and it turns out you're not very sensitive to dark energy, but you're very sensitive to matter, to how much gravity, attractive gravity there is in this experiment. And so I want everyone in the audience to look up there and figure out, is model 1, 2, 3, or 4 the one that looks like the real data? All right, so let's do vote. Who thinks 1 is the correct one? Who thinks, and you're not allowed not to vote here, okay? That's one of the tricks my students do all the time. So with that in mind, who thinks 1 is correct? Who thinks 2 is correct? Who thinks 3 is correct? Who thinks 4 is correct? All right, well, the good news is you guys are almost as good as a computer. That is the correct answer. And it tells us that 30% of, it tells you that you're essentially 30% of the way with normal gravity, stuff that attracts, of the way to the universe being just right. So the way we keep track of how much material there is in the universe is by essentially measuring how much stuff there is compared to the amount to make the universe geometrically flat. And that measurement told you that the amount of stuff, attractive matter in the universe, was 30% of the way there. So that was the first measurement. Second measurement, I should say that 30% is an interesting number, but even more interesting is that's sort of 5 times more gravity than you can account for in atoms. So that number, 5 to 1 atoms, has been seen, it turns out, since the 1930s. Everywhere in the world we look, we see something we call dark matter. All right? So that's a different mystery, more or less a different talk. We'll talk a little bit about it in a second, but that's how much material there is in the universe that's attractive. The other experiment, I should say, comes from the cosmic microwave background. Now that picture is the entire sky that we're looking at, and what we're looking there are sound waves that are rippling around the universe. So when you look at those sound waves, it turns out you can learn something. Why? Because if, for example, you have a pond and you throw a rock in it, if the pond is made of water or made of molasses, the waves look different. And so you can figure out what the pond is made out of. It turns out the Big Bang, very conveniently, essentially did the equivalent of throwing gravel into the universe, which put a bunch of waves that rippled around. And then when the universe, 380,000 years later, when we take a picture of it in the cosmic microwave background, we can see what the wave action looks like. And this provides us an amazingly precise measurement of the composition of the universe. It turns out, what we find out, is that the universe is about 5-to-1 atoms to dark matter. A very interesting thing back then. The other thing you can do is sound waves travel at a speed. And so we know essentially how long a sound wave is in the earliest universe. It's essentially how far sound can travel in the universe over 380,000 years. So that is the size of one of those bumps. And by looking at how big those bumps appear, it turns out we can measure the shape of the universe. Why? Because when you look at a universe, if objects are traveling through curved space, they appear a different size than if they're traveling through space that is not curved. Think of it as being like looking in a curved mirror, because the whole universe acts as a giant lens. So we can actually look at the shape of those bumps, the size of those bumps, and measure the shape of the universe. If they're very small, then the universe is infinite. It's curved like a saddle. If they're very large, then the universe magnifies the bumps effectively. And if it's just right, it's in between. And when we look at those sound waves, we find that to within a very, very high accuracy, the universe is just right. It's flat. So that turns out that when you look at the shape of the universe, the amount of stuff that makes the universe just right can be any type of material. It can be material that causes gravity to pull, but it can also be the material that causes the universe to push. So that allows us to do a little bit of cosmic subtraction. Everything adds up to 100%, and then from the gravity, we know 30% is gravitationally attractive, and so that gives us 70% mystery matter. The same mystery matter the supernovae are saying is dark energy that's pushing the universe apart. Now it turns out, since 1998, in the 17 years, we have been able to make many, many experiments, and every single one of them, turns out, has found exactly what this model, a crazy model, of which 95% of the universe is stuff we don't understand. So our model of the universe is 5% of the universe are the atoms. That's the atoms, the only things you've ever known and seen other than light. Well, those are the atoms. 95%, 70% of being this dark energy, energy that's part of space, 25% being dark matter, stuff that has gravity, but seemingly, essentially can just travel right through things and doesn't actually show itself, it's invisible, except for through gravity. So this is quite a messy description. And many of you should be thinking right now, if you got to make up 95% of the universe, doesn't that mean you just don't know what you're doing? Perfectly reasonable call. But what's remarkable is I said this predicts everything we see. And like it or not, science is all about prediction. And when you have a model that predicts everything you see again and again and again, well, that is the basis of what we say reality is. Now that might change a bit over time as we learn more, but in the same way that we don't give up on Newton's laws of gravity, just because Einstein came along, I think you'll find that this model actually lives through time as well. So at this point, people often ask me, why do we do this? Especially members of parliament. And I always like to say, because it's beautiful. It tells us about our place in the universe. And in which case they say, okay, why do I pay for this? At which point I say, well, because it's useful. This is Tim Berners-Lee working at CERN, who helped develop the World Wide Web. This is John O'Sullivan, an Australian astronomer looking for evaporating black holes, developer of Wi-Fi. These two things have changed humanity and are just two of the things that have come out of astronomy. Not intended, but they're useful. Your digital camera, well, Turns out CMOS was developed for sending probes to Jupiter. That's the thing that's made us each have a digital camera in our phone. We also have contributed to maybe things that are less useful, like airport security detection equipment and other things. So we do astronomy because it's interesting, but we pay for it because it's useful. So what's the future of the universe? Well, that's a big call. But the future of the universe is really a battle for domination of the universe between dark energy, which pushes, and dark matter and atoms, which pull. And the dark matter plus atoms, well, as the universe expands, they become less and less strong over time because their density becomes diluted. On the other hand, dark energy is part of space itself, and so its density doesn't change at all. The universe gets bigger, it's just part of space, it's always there, which means dark energy will, over time, become stronger and stronger compared to dark matter and atoms. So that tells you that the future of the universe is dark energy. Dark energy has already won the battle of domination of the universe. The more the universe expands, the faster dark energy wants to push it apart. So the universe is going to be expanding faster and faster over time, so fast that in the future, stuff that we see in the future will become invisible because the material, as it travels through space, will be stranded by the expansion of space. That is, imagine a galaxy we can see today. A photon trying to get to us in the future will try to get through space. Space will be created, and it will literally get stranded in the expansion of space. Things we see today will disappear in the future. This is a scary future. Now, unless you're worried about the very distant future, sometimes we are, worry about things around us. This does not mean you are going to be expanded with the universe. And that's because that's the density of dark energy today. That's the density of the Earth. The Earth is not expanding right now. It stopped expanding. Gravity overpowered not just dark energy, but the expansion of the universe 13 billion years ago here. So our part of the universe is not expanding because attractive gravity won. And indeed, our Milky Way, and indeed, even the nearest few galaxies, are all within a sphere where attractive gravity has won the battle of the universe. In the future, you can expect, for example, the Andromeda spiral and our own Milky Way to merge together to form a huge new galaxy. But when we look out to the distant galaxies beyond us, those parts of the universe will be accelerated away. So we will look out onto stars, which will eventually all die, but nothing beyond that. So the reality is, we don't know what dark energy is, and a theorist can always rewrite the future. The only way to absolutely know the future is to be omniscient, or to kill all theorists. I recommend the first. So anything is honestly possible, but when it comes down to common sense, unless, for example, the dark energy suddenly disappears, then we are looking forward to a universe that will, at an ever-increasing rate, expand, fade away, leaving myself and Mark permanently unemployed in the future. Thank you very much.
Thank you, Brian, for this wonderful talk. And I would now like to open the floor for questions. So.
Don't be shy. The first one's always the hard one. Excellent. Do we have microphones? No.
I can talk loudly.
Okay.
Is there a time estimate of when we won't be able to see the background radiation anymore, for example, because
Yeah, so it all depends on how, so is there a time when things really fade away? So one of the features of relativity is that things fade away and technically are always visible. They just become infinitely faint. But let me put it into a different way, not in terms of the microwave background. Let's put it in terms of a galaxy. In about 100 billion years, the nearest galaxy to our own will be more distant than the most distant known galaxy now. Okay? 200 billion years, things are so far away that you would just never be able to see anything. Now, 200 billion years is a long time, but in terms of a universe that apparently is going to exist forever, you have this interesting play out of history. 1 trillion years from now, there will still be some stars in the Milky Way. 1,000 trillion years, all the stars will be dead. Then black holes will evaporate. It turns out eventually we think the atoms themselves may become unstable. And as that happens, slowly everything we know disintegrates, and you eventually end up with every subatomic particle separated from every other subatomic particle in this accelerating universe, so that every subatomic particle is in their own voidance where it's the only thing eventually that exists. So that's long, long time in the future. Trillions upon trillions upon trillions of years.
Yes. Other questions? Yes.
So this,
Let's wait for the microphone.
So this 30%, 70% ratio between gravitating matter and the energy pushing it matter apart, how does that correspond, or does it correspond at all, between the repulsive electrostatic forces and what we call the strong force in the nucleus of an atom?
It doesn't seem to correspond at all. Sorry, God, I really do believe that to be true. No, that's one of the things. This 70% dark energy is bizarre. It's just a number that's come out of nothing. It doesn't fit in with the knowledge of the rest of physics. It turns out that if you do take the fundamental forces of nature, which provide sort of a scale of energies in the universe, and you use quantum field theory, and quantum field theory allows essentially quantum fluctuations, which are equivalent to energy, to come in and out of existence for very short periods of time. And then you go through and you take each one of those quantum scales and you add it up, because at any given time, these quantum fluctuations, as we call them, can only exist, but they always have positive energy. And you ask how much energy should be in a cubic meter of space, it turns out to be 10 to the 90 times more than what we've measured. That much material would mean the universe would have never ever been able to form galaxies. We could never exist. So that's one of the big issues we have in physics, is quantum field theory essentially doesn't seem to make sense of why dark energy just isn't so big that we would have never existed. So what they always do is say, well, if it's going to be that far off, there must be zero for some reason. What we have is that a decimal place, 90 zeros and a 1 times less than the prediction is how much we've measured. So that's a problem. That's a fundamental problem of physics we do not understand. But dark energy does not make sense within the rest of physics at this point. It really is one of the big mysteries.
Yes, please.
Thank you. I'm sure there was a reason, practical reason why the sound was funny just now, not a divine one. I'm a linguist and not a scientist, but I just wondered if you personally would think that well, I don't know what your beliefs are or whatever, but when I look at the universe from my back garden, I see the majesty of God and the wonder of it, and I find it fascinating to listen to you, to know the actual size and all the dimensions and everything. But I just wondered if you, or anyone here, if you looked in a mirror, not a curved one or a fancy one in a telescope, but if you looked in your bathroom mirror and you could see your soul and your heart, would you consider it important enough to, well, let's put it another way. Would you ever realise that it's more important to see and to do something about how far our hearts are away from God than how far the Earth is away from the nearest galaxy? That's just a philosophical question, but you might not.
Okay, well, let me take my own, people have different ways at dealing with it. It's what it's like to be human in the universe. People have faith. People have a set of rules that they live by. So I'm not religious. I'm not anti-religious. I'm just not religious. And what I deal with is I look to understand the universe around. And that makes me understand my place in the universe. And that is the approach of a scientist. It is not necessarily, some people disagree with me, but I would say it's not necessarily at odds with a faith-based approach. There are many astronomers who are very deeply religious. There are many who are not. But in the end, it comes down to understanding how you exist in the universe. And that's a fundamental part of being human. And that's why when you look back at the earliest humans and what they decided to put on cave walls, they put pictures of stars. They wanted to understand the universe they lived in. The fundamentals of science started in astronomy. It's always been part, trying to understand ourselves. So I think that's deeply part of being human, but it's also a very personal way that each of us deals with being human. And so from my perspective, as long as people respect my way, I respect their way, and that's the best we can do.
Any other question? Yes, over there. Then there.
What's next for dark energy, and can we do anything with it?
Could you say it again?
What's next for dark energy? Kind of in research of dark energy.
Oh, so what's coming next after dark energy? Or what are we going to do? I do not know how we're going to solve dark energy. What we're doing right now, and something that Mark and I work on together, is we're making better and better measurements of how the universe is expanding over time. And those allow us to look and say, is Einstein's prediction, is that exactly what we see? And thus far, like most things that Einstein did, he got it exactly right on the first time. He did make some mistakes, but not in this, it seems. So we're going to continue to measure it and see if we can find some deviation from what Einstein predicts. If we see a deviation, then we can start thinking about, for example, a new class of particles that are analogous to the Higgs boson, but a little different. That would be one way to solve the problem. But as long as Einstein is right, we're stuck. We're stuck with the fundamental idea of what dark energy is. And so what I think we need is a brilliant mind to come along and think in a higher way how dark energy fits into physics as a whole. And it's probably going to involve quantum field theory or some variant of it. And that's wound up into string theory, for example. And whether or not string theory eventually gives us an answer is to be determined. But I think that's the type of breakthrough we're going to need, is we're going to have to understand from a theoretical point of view what the place of this dark energy is. I'm not convinced it's going to happen in my lifetime. But of course, I didn't think we were going to discover the universe was accelerating. So what I think, again, has no bearing. You do your best and see what happens.
Yes, and then back there.
Yeah?
Oh, you answered, I'm afraid that was...
Okay.
Yep.
You're exploring the expansion of universe, that's clear. What the picture in your mind you have when we're talking about expansion, there is no center of expansion, that's clear. Well, what picture do you have in your mind to understand that there is no center of expansion?
All right, well, as I said, visualizing expansion of space, especially when there are 4 dimensions involved, one of being time. But I think the most relevant view I have is twofold. One is if the universe truly is infinite. The universe is truly infinite, then you just think of it as this giant grid that goes out in all directions, and the grid is moving out over time. It's just expanding, and it goes without end. And to the level you can come to grips with infinity, you can deal with that. Just means as the universe expands, you got to think of about like the little number lines you did in grade school where, you know, 1 goes to 2, and 2 goes to 4, and 4 goes to 8, and you just do that out to infinity. A finite universe, which is allowed, is the easiest way to think of as the 2-dimensional analog with a balloon. So you take your balloon, you put your little stars or galaxies on it, you blow the balloon up. The Big Bang is the center. It's when the balloon is really, really tiny. So as the universe expands, it's expanding out in this dimension, this 3rd dimension, which we can see. Well, that's like the future. That's time. So you're expanding into the future.
But there is no center.
Well, but the center is the Big Bang. It's the beginning. So there is a center of our universe. It's called the Big Bang. And that's because our universe inherently has time associated with it. So you got to think of that extra little bit of time. Now, the part about the balloon is you don't get to see if we're in a big, if our universe is the shape of a balloon, it's a really, really big balloon, and we can only see a tiny little patch of it right now, right? So that's the best analogy, but then you got to add an extra dimension in it, and I'm afraid I'm not insane, so I can't do that.
I guess you haven't mentioned anything about inflation yet.
Yes.
Cosmological inflation, which is widely believed to have happened in the very first moments of the universe, and also involved accelerated expansion, not unlike dark energy. So do you see any connection there?
All right, so as a background to the audience, when I described the Big Bang, I described the Big Bang as essentially throwing gravel in the universe. That idea comes from the theory of what we call inflation. The evidence is that our entire universe we see now came from something, you know, smaller than a golf ball right after the time of the Big Bang. And as the universe expanded exponentially, something that it appears to be doing again right now, it went from being the size tiny, smaller than a golf ball, to being much, much bigger than everything we see today. These quantum fluctuations, which happen at the scale of smaller than atoms, are blown up to being the size of the entire universe. Where those fluctuations are essentially bumps and wiggles in the universe. Those are the gravel that the universe was born with. This fixes, it turns out, many problems we have in our universe. It tells us why the universe is the same temperature there and there, because it all came from a place that was in contact. It tells us why the gravel was thrown into the universe. It also tells you that the universe should have been born just right, because when you exponentially magnify the universe, if it was started off with a potato chip, it ends up looking like a very flat piece of paper afterwards. But for some reason, the universe stopped exponentially expanding and then was created into the universe we see today. This bout of exponential expansion now is at a very, very different energy scale, so it's very hard to figure out how it would be connected to what happened at the time right after the Big Bang. People have tried. It would be great to unify those with one idea. The problem we have is, one of the reasons you win a Nobel Prize is because about 10,000 papers have been written about our discovery. And those ideas are 10,000 ideas to explain it. And that may sound good, but that means we have no idea what's going on because we have 10,000 ideas, none of which agree with each other, and none of them are particularly different. So there is no easy way that I know of to connect what happened back then with what's going on now. The basic idea that dark energy can exist and work as general relativity, well, we seem to have proved that just by seeing what the universe is doing now. So it may be the same type of piece of particle physics at a completely different energy level, could be something completely different. We do not know. So again, a big mystery still.
Yes, over there in the center.
Yes, you said that when you ask for money, one of the reasons is that Wi-Fi and the World Wide Web were created, but these are just collateral reasons. It doesn't mean that that if we had invested this money in another place, this place would have also created Wi-Fi or World Wide Web. So could you give me another reason?
No, I'm going to give you a good reason, because if you empirically, I'm married to an economist, so if economists go through and they look at the benefits that you get from investment in things like science, it turns out you get a very big return on your investment if you're a government. Better than anything else a government does consistently from the empirical economic analysis. So I'm not going to give you another reason because it's a very strong reason. There's nothing else that a government spends that gets a higher return on investment. That's from the empirical analysis. Now, we have done the experiment as a society where we didn't invest in things like arts and sciences. It's known as the Dark Ages. For 800 years. So we can do that experiment again, but I don't recommend it. And all I can say is if you do the economics, and the empirical analysis, it's very strongly in favor that this is a good thing to do. How much we spend, that's a harder amount of question. But you're a brave person to say you should not invest in science. Because when you do invest in other things, it turns out the return of investment is lower, even infrastructure. Doesn't mean you should put 99% of your money, because then you wouldn't get a good return. But paying 2.5% of your gross domestic product seems to be a pretty good investment for a country by economics.
Yes, over there.
Why is it in our specific region of the universe that normal gravitational attraction wins over dark energy?
So why? Okay, so our part of the universe was born a little denser than the average. So our part of the universe 13.5 billion years ago slowed down, and because there was a lot of gravity there relative to the average. And so that meant our universe stopped expanding, and our little piece of the universe went into essentially a crunch. That's what formed the Milky Way, which formed Earth. So once the universe has stopped expanding, dark energy's density just stays where it's at. It's part of space. But the Earth's density is 30 orders of magnitude higher. So dark energy can never restart the expansion of the universe again. So that's why whenever you get lumps and bumps in the universe, the lumps collapse down to form galaxies, and the empty regions in between them, where dark energy right now has a higher density than the atoms of the gravity, Well, that stuff gets pushed away. So you end up with these little clumps being pushed away from the other clumps. So each place where there's a galaxy, that's a place where the universe was denser than average and quit expanding. And it's the space between them that get pushed apart.
There was another question. Yeah, same. And yes, over there.
So you spoke about the possibilities of our universe, one being finite, it's like a sphere, and you end up sort of almost orbiting around, the other one being flat. It's only been around a certain amount of time, so at some point there must be a cutoff, and I know obviously it's a crazy theoretical side, but what's your personal view on what could lie the other side of that?
So I think what you're saying is, no matter what shape the universe is, there's stuff beyond the stuff we can see right now. Is that more or less what you're saying?
Well, yeah, I mean, it's expanding. It doesn't matter what shape and what's, form it's taken. It's only had a certain amount of time that the space can be expanding.
Yep.
So what do you think lies beyond that kind of boundary?
Right.
It used to be a case of there was this theory of multiverse, which is very much fictional, but I've seen a lot now that sort of people almost believe in it a lot more.
So the answer is we don't know, but I'll give you a few examples of how we don't know. So we know our part of the universe, of which light can get to us for 13.8 billion years. That's the time since the Big Bang. We have every reason to believe that there is a lot of universe beyond the part we can see. And the reason we can't see it is because we just haven't had long enough for that light to get to us. The problem we have is the basis of science is testing. And how do we test something which there is no observational way of getting any information about? Well, it turns out that, for example, if there was the universe suddenly changed just outside of our boundary, it would affect a circle of material that we could see. But I can put it far enough away where that's not true. So one of the things is that our universe may well be infinite, or it may be finite and just really, really big. So you don't know, as you go further and further away, we don't know what that universe is like. It could be exactly like our universe, or it could slowly drift away and be a bit different than our universe and have different physical laws. That's one manifestation of a multiverse. A completely different manifestation of a multiverse is that this period of inflation, well, that's the entire universe. And that one little part of that universe, suddenly something happened, quantum fluctuation happened, and the universe, essentially our universe, was created out of an infinite universe as sort of a little bubble. And that bubble is the part of the universe that we see, and it goes on, at a scale much, much larger than what we can see, but it's there. And it's surrounded by a bunch of universe which is exponentially expanding. And these little champagne bubbles, which end up being the sizes of universes, pop off everywhere. But because they're embedded in a universe that's exponentially expanding, light cannot get from one point to the other. And so you would have an infinite universe that's expanding exponentially with these little universes popping off, none of them able to see the other ones. That's another version of a multiverse. I don't know how to test that either. So that's really an area of metaphysics at this point. Because it's not easily testable. But in the end, there may be ways to test them. We don't know. That's what the theorists who are working on those are working on. But I can't really say anything other than say these are ideas, but they're not testable yet, so I don't know what reality is.
Any other question? Yes, over there.
You spoke about the Big Bang, but you didn't speak about what provoked the Big Bang. I know there are many theories about it, but I'm curious what your theory is. and also if you think that it could be ever proved, like empirically proved what provoked it.
Yeah. So I just gave an example of one idea what the Big Bang was. The Big Bang was our universe being formed out of an exponentially bigger part of a universe. The reality is we don't know what the Big Bang is. We only know what happened after the Big Bang. So people will tell you time was created in the Big Bang. I'm not even prepared to tell you that. I don't know what the Big Bang was at all. I only know what came after. And right now we know pretty well what came after, a few milliseconds after the Big Bang. And we have reason to believe we may even start understanding things back to 10 to the minus 35 seconds after the Big Bang, if we could make certain measurements in the cosmic microwave background. So the way we might understand what the Big Bang is if some brilliant theory comes out that predicts what we see in our universe and tells you what the Big Bang is. We do not have that theory right now. So I'm an agnostic when it comes to what the Big Bang is. I don't know. I'm not ruling out us being able to understand it, but at this point, it's really anyone's guess, because we only know what's happened afterwards.
Any last question? Yes, back there.
Just wait for the mic. My poor ears aren't very good.
This might sound a silly question, but when you're talking about multiverses, what about the many worlds theory, which I see in so many sci-fi TV shows?
Okay, so the basic idea of whether or not, for example, there's a copy of you asking me this question, and everyone here being identical in the whole universe, comes down to a question of what I would say complexity versus infinities. So how complex is this situation? How many variables are there? It may well be infinitely complex. If it's infinitely complex, and I have an infinite number of planets in the universe, then I need to understand those two infinities, and we don't. So my own hunch is this is a unique moment and you're unique. But I could be wrong.
And with this note, I think we should thank Brian again for this very interesting talk.
Thank you.
Outside, and also some PhD students put posters with their research, so please go and look at them as well and talk to them. And thank you all for coming. And also very nice answers.